In number 16, we're looking to see what product is obtained when we treat benzene with the following. So benzene with nitric acid in the presence of sulfuric acid will add a nitro group to the benzene ring. In letter C, we're looking to add chlorine in the presence of aluminum trichloride. That will add 1 chlorine to the benzene ring. Alright, so if we treat benzene with nitric acid and sulfuric acid, that again is going to give us our nitro group. If we follow that with zinc and HCl, and sometimes sodium hydroxide follows that as well, and that all goes together to reduce the nitrogen, or the nitro group, to an amine. Here we are trying to identify what reagents are used for each of the transformations. If I go and start from the left, to add a bromine, I need Br2 and FeBr3. For chlorine, it's the same thing, Cl2 with AlCl3. You can also use FeCl3, you just want those halogens to match. For the nitro group, we had HNO3. And then to reduce that, that's zinc HCl. For the SO3H group, we use fuming sulfuric acid. To add a methyl group, this is CH3Cl, AlCl3. That's the Friedel-Crafts alkylation. To make it the benzoic acid, we can use the Jones reagent. If you want to add bromine, or 3 bromines to make that CBr3, we can use XS and BS. For this acyl group here, we'll just take whatever's on the other side of this group and add chlorine to it with AlCl3. And to reduce it, it's zinc amalgam, HCl, and heat. Okay, here we're looking at toluene and monobromination. So if we have toluene, that is benzene with a methyl group. I'm going to add Br2 and FeBr3. A methyl group is the same as an alkyl group. That is an activator. And that activator is an ortho-para director. So we should see a product where we have the ortho product. And we'll also see the para product. When ethoxybenzene is treated with nitric acid and sulfuric acid, 2 products are obtained, which have the molecular formula C8H9NO3. This is ethoxybenzene. We have HNO3 and H2SO4. The ethoxy group, the O, is immediately bonded to the benzene. So this is an activating group, which is an ortho-para director. So we'll get the 2 products. One will be the ortho, plus the para. In number 10, we're going to look at what is going to get added next, or where is it going to get added next. And remember that activating groups are stronger directors. And halogens always lose. So in B, we have an activating group, the methyl here. This is deactivating or electron withdrawing. As is the other nitro. So the methyl group is the one that's directing. The para position is taken, so it will add, the next group will add to the ortho position. In G, we have two electron donating groups and a halogen. The halogen loses, so that one's not directing. We can direct to this para position, which is ortho to the other group, or this para position, which is ortho to the other methyl group. In I, we have all kinds of groups here. The benzene is in the middle. This ketone right here is electron withdrawing, as is that one. But then we have this alkyl group here, or these alkyl groups, and those are electron donating, and they're ortho-para directors. So the ortho position to that is this one, which also happens to be meta to the carbonyl. So we're going to have a match situation there. All right, so if we're looking at reagents to add a nitro group on a carbon that is already there, this one we would need to use a blocking group because the nitro group that we're adding is ortho. So to add the blocking group, I'll use fuming sulfuric acid. And that will put my group over here. Then I can add the nitro group. And that will go ortho. And then to remove the sulfonate group, we just use dilute H2SO4. In letter B, there is an isopropyl group and a bromine that is para. Para is often preferred over the ortho because of sterics, so this one we can just put the bromine right on. Okay, here we're looking at what's going to happen with nitric acid. A nitro group is electron withdrawing, and it is a meta director, so we should see one product, which would be meta dinitrobenzene. This carbonyl is a carbon bonded to double bonded to an oxygen, so this is electron withdrawing, which is also a meta director. So we'll add the NO2 group meta. With an OME, these electrons can donate in, so this is electron donating, or an activator, which is an ortho-para director. We'll get two products here. So the group that is on the ring is the one that is driving the bus, not the group that is getting on the bus. Here we're treating these products with sulfuric acid. So phenol, the OH is an activator or electron donating group. This will be an ortho-para director. So we get two products. We have nitrophenol here. It's ortho-nitro. And here the ortho position is already blocked. So we can add our sulfonate group to the para position. And the activator is the one driving the bus here. And in this case, they're working cooperatively because that nitro group is also a meta director, and that sulfonate group is meta to the nitro group. This is para-ethyltoluene. They are both orthopara directors. So we might get a mixture of products here. And these we're treating with chloromethane and aluminum trichloride. We are assuming monoalkylation, so we don't have to worry about polyalkylation. The methyl group is an electron donating group. Halogens always lose. So we can get a methyl group para. You can also get a methyl group that is ortho on the other side. In this case, these both carbonyls are meta directors. So we'll add a methyl group. Actually, this would be a meta director. But this is also a strong electron withdrawing group, so we'll actually see no reaction here. We can't do a Friedel-Crafts with a strong electron withdrawing group. This oxygen here is donating. This methyl is donating. We'll see in orthopara, since the oxygen is a stronger donor, it will be ortho to that. And also the para. All right, here we're predicting the products of each of these reactions. We have a methyl plus a Br, and we're going to add an NO2 group, and it's going to add to the ortho position because we have an electron donating group, and the para position is blocked. So NO2 will get added first. And the zinc HCl plus NaOH step will reduce the nitro group to an amine. Here we have two methyl groups. We can add the Friedel-Crafts here to the ortho position. And this one is okay because the methyl groups are weakly activating. And the zinc amalgam will reduce that. In this one we have the addition of a methyl group. And this will be adding para plus ortho. And then excess MBS will brominate at the benzylic position. Here we're looking at proposing a synthesis. Things to observe: I've added an ortho-bromo and a para-nitro. If we look at our starting material, this is anisole. We have an oxygen here with alone pairs. It's not multiply bonded to anything else. This is an electron donating group, and that is an ortho pair director. It just happens that both of our groups that we need to add are ortho and para. And if we strategize, we don't have to use a blocking group. If I add my nitro group first, it will go para first, because that is preferred sterically. And then I can add the bromine. And if I had done the bromine first, I would get a mixture of ortho and para, and you'd have to worry about separating it. Otherwise, if you really were bent on adding that bromine first, you could use the blocking group and then add the bromine, remove the blocking group, and then add the nitro group. In this one here, I notice that I have oxidized my benzylic hydrogens. And I have an ortho nitro. Okay, so in this case, I do need to use a blocking group because my nitro group needs to be ortho. So I am going to add my blocking group. So I have SO3H. And then I can add my nitro group. And the thing that is driving the bus here is the isopropyl group, because that's the activator. The SO3H is the deactivator. And I want that to go ortho, and that works out just fine for me. Now I need to remove my blocking group with dilute H2SO4. And then I can oxidize with permanganate. We don't want to oxidize too early, so if you oxidize your group right after, or first, let's say you oxidized here, we would get benzoic acid right off the bat. That benzoic acid is an electron withdrawing group, or a deactivator, which is a meta director. And we want our group to be ortho to the group. So make sure that you do the blocking group and then oxidize last. All right, here's another exercise in predicting products. Here we have electron donating. This is electron donating, as is this one. The methoxy is a stronger donator because of the lone pair here. So that's going to direct ortho or para. In this case, it happens to be ortho to the electron donating group, and it's less sterically hindered over there. So the para one will be preferred. You could also get the other product with the ortho. In this one, we have a bromine, which is the loser. This is the electron withdrawing, and we have a strong activator here. So that's an ortho para director. The para position is blocked, so we have to go there. So we're looking at synthesizing benzene here. I have a acyl group, nitro, and a chlorine. They are all meta to each other. The nitro group, if I put that one on first, I'm just thinking here, if I put the nitro group on first, that's an electron withdrawing group, which is a meta director. And that would be okay because my acyl group is meta and the chlorine is meta. The chlorine is electron withdrawing, but this is an ortho para director. So I don't want to put that one on first. Because it is an ortho para director. And then I have this carbonyl here, which is also an electron withdrawing group, which is a meta director, and again both things are meta to that, and the only thing that we want to do is use this one first, and that is because once we put the nitro group on, we won't be able to add the Friedel-Crafts reaction or add the reagent there, so we want to add our carbons first. So you can just take whatever is on the other side of the carbonyl, add a chlorine, then I can add the nitro group. And at this point you could either add the chlorine or the nitro first. It doesn't really matter because the carbonyl carbon is going to be the one driving the bus. And then add the Cl. So like I mentioned, the chlorine could be added first or the nitro group could be added first there. Alright, in this one I have lots of things to add. There is a carboxylic acid, nitro, BrCl. So I'm just going to go around the ring and see where my groups are being directed. A carboxylic acid, or COOH, is the same thing as this. This is electron withdrawing, and it is a meta director. A nitro group is electron withdrawing, a meta director. Bromine is a para ortho para director, as is the chlorine. So we can do a couple of things here in different order. The bromine and chlorine are going to add ortho to each other. If I put the benzoic acid on there, or that carboxylic acid on first, that one is a meta director, which would be okay for the chlorine and the nitrogen, but not the bromine. And the nitro group, if you put that on first, that's okay for the carboxylic acid and the chlorine, but not the bromine. And also we can add the Friedel-Crafts with the nitro group first. So again, with this one, there's a couple of different ways that you can do this one. If I wanted to start with adding my carbon first, we don't have ways of adding benzoic acid directly or that carboxylic acid, but we can add CH3Cl. and then oxidize it. But one thing that you want to remember is that I do have a bromine group that is para, and if I oxidize it, that's going to be a meta director. So this is an ortho para director. So the methyl group on here is an ortho para director, and I need that bromine to be para. So I'm going to leave that group alone right now and add my bromine first. And now I have the ortho position. And if I try to add anything else right now, that's still going to direct my groups ortho or para, because that methyl group is the one directing. So because the other two groups are meta directors, I want to switch where it goes, and I can oxidize that position to benzoic acid. And that's going to change my director. So now I have a meta director. So I can go ahead and add my chlorine or nitrogen. The order at that point does not matter. And then add the nitro group. And the bromine doesn't get to drive the bus because it is a weak deactivator. So that will give us that product. So again, between the chlorine and the nitro group getting added, either of those can happen in either order. So if you wanted to add the nitro group first, you could, or you could add the chlorine first there. That would not change the synthesis. We did say that we don't want to add nitro first, because then we can't do the Friedel-Crafts. Okay, so another thing that you could have done is actually you could add the bromine first. That one is also an ortho para director, and because it's the only one on the bus, that one will drive. Then we can add the CH3Cl, and it's okay to do Friedel-Crafts with the halogen on the ring. That is an ortho para director like we mentioned. And then once you get to this point, you can just pick up the synthesis there. So that's another option. In this last synthesis, I have a CH3 group, chlorine, and a nitro group. This is electron withdrawing. It is a meta director. I have a carbon involved also, so I don't want to add the nitro group first. I have a CH3, which is an ortho para director, and a chlorine, which is an ortho para director. If I think about putting the carbon on first, then the nitro group is para to that, and the chlorine is ortho, so I can just do just that. There's not a need to kind of maneuver too much around. So add your carbons first. And then we can add the nitro group. That will be preferred, the para position will. Then we don't have to worry about the blocking group. And then add your chlorine. That will be ortho to the carbon which is driving the bus.